The problem statement is called count good nodes in a binary tree. We can see that this one is a relatively new problem, a medium problem, and also a very well-liked problem. On top of it, this has been asked at tons of different companies. So let's pay some attention that what the question is asking us to solve. Basically, we are given the root of a binary tree and we need to return the number of good nodes in a binary tree. The question is, what the heck is a good node? Well, a tree node is deemed good if in the path from root to that particular tree node X, there are no nodes with value greater than X. If that is the case, that node is a good node. So let's try to understand this with an example. Currently, we can see that there are 5 different nodes or 6 different nodes in this particular tree. Now we are being told we need to find the good nodes. The definition of a good node is that path from root to any particular node. If that particular node contains the maximum value, then it is deemed good node. So let's try to see what are the good nodes, starting with the root. Now root in itself is a good node because path from root to root is the biggest value. So we find one good node. Okay. Now let's consider value number 1. What is the path between root to value number 1? This path. Is 1 the largest number on this path? No, which means 1 is not a good node. Then let's consider the path 6. So for 6, the path is 5, then 1, and then 6. So in this case, 6 is the largest number from the direct path to the root, which means 6 is also a good node. So let's mark that. Once again, now we found everything we could. Let's try to move to next value number 5. So is 5 a good node? Yes, 5 is also a good node. Why? Because the definition of 5 is that from root to that particular X, there are no nodes with value greater than X. So in this case, the nodes we have is value number 5, 1 and 5. So there are no other nodes that has value greater than 5, which means 5 is still a good node. So we will also mark this as good. Then we will jump to value number 7. So once again, the direct path from 5 to 7 is this one. So in this case, 7 is the largest node. So 7 is also a good node. And next value is once again 7. So once again, even in this path 5, 7 and 7, there are no values greater than this 7 as well. So 7 is also a good node. So in this case, in total, we found 1, 2, 3, 4 and 5 good nodes amongst these 6 nodes. So we need to return 5 as the answer. And this is what the problem statement is asking us to solve. So now let's try to understand the logic on the solution we can build for this particular problem. The logic is quite straightforward, that we need to iterate over the given tree in some fashion, and we will have to keep track that around this iteration, what has been the largest value we have been able to find so far, keep track of it, and using that particular value, we are going to make some important judgment calls. So the logic we are going to do is that we will have to iterate the given tree in depth first search fashion. Why depth? Because we will have to keep track of the entire path from root to any particular node. So for that, we will have to go into the depth first search order. Now, what are the considerations? Number one thing is, first we are going to check the root or at any given position, because first we are checking the root, then we are checking for its left entire subtree, and then right entire subtree. Same thing we are doing at every single level, that first we are checking that for this particular root, whether it is the largest number. After understanding this, we are checking its left subtree and then right subtree. So basically we are doing the pre-order traversal in this case. And pre-order traversal is quite straightforward. The logic is root, then left, and then right subtree. So we are once again going to do a pre-order traversal, in this case in depth first search fashion. We are going to keep track that what has been the maximum value we have been able to find inside the current path. If the current node is equal to or greater than the maximum value we have been able to find, so in this case we are going to deem this node as a good node. So we also need a variable to store the good node as well. So let's assume that, okay, we are going to have our count variable to store all the good nodes we have been able to find so far, and this is the whole solution we need to create. So let's try to understand, or let's try to iterate over our given solution, and let's just arbitrarily give some values to these particular trees or these particular values. So in this case, we can see that these are the different values. Now let's start with value number 3. 3 in itself is a good node because we are doing the depth first search pre-order traversal. We are going to take care of the root first. Okay, now we took care of this root. Now let's take care of the left child. So left child is once again 1. So once again, even at the left child position, we will have to follow this position of root left and right. So once again, now left child in itself is a root. So we have value number 1. What has been the, and also we have our maximum value we have been able to find on the current path. So maximum value so far has been 3. This value is 1. So current node is not greater than maximum value, which means this is not a good node. Now we will need to check for the left pointer. So left pointer is once again 3. So 3 is same as the maximum value on this path we have been able to identify. So we are going to mark this 3 as the answer that we have been able to find so far. Now 3 is also going to be a good node. So we are going to add our count of good nodes. Now we are going to do a backtrack. Now for the backtracking, once again, we have a right node that we haven't checked. So we are going to take care of the right node as well. The value of the right node is 5. So currently at this particular position, the right node is actually greater than the maximum value we have been able to identify. So we are going to store, once again, count this 5 as a good node as well. Apart from doing that, we will also have to update the maximum value we have been able to identify, but this particular node does not have any subsequent child nodes of his own. So because it does not have any child node, there is no point in updating the value of the maximum node. But say for an example, if we did had one more child like this, where we need to check for the value of this node number 6, then this 5 would have been the maximum value we have been able to identify so far, but that is not the case. Once again, coming back, now we took care of 5 and we took care of 3. It does not have any children. We are going to do the backtrack. We already took care of 1, which means now we have to taken care of this entire left child. Once again, in our pre-order traversal, we took care of the root very first, then we took care of the left child. So this is the entire left child portion of this root. Now we need to take care of the right child. So once again, we are going to do the same thing. We are at position number 4. So we are going to first check that whether 4 is a good node or not. So in this path, the current maximum value we have been able to identify was value number 3. So 4 is a good node. But in this case, because we are checking for the subsequent children of 4, we will have to update the maximum value we have been able to identify along this path to value number 4. So this is the maximum value we have found so far. Next value is value number 2. So 2 is not is less than the maximum value we found. So 2 is not a good node. So in this case, we found in total 4 good nodes. So we are going to return 4 as the answer. And that's it. This is the whole solution that we need to return. Basically, we need to understand that why we need to use DFS in this case, because we are going in one particular direction. We will need to keep track of the maximum value at any given track. And we also have to do the pre-order traversal because we are following the principle of root, then left and then right. And you can do this recursively or iteratively, it's up to you. We will see that in the coding. If we see time complexity, it's pretty straightforward. It's going to be big O of n because we are iterating over every single value. In terms of space complexity, if you use the recursion method, it will take big O of n. If you use iterative method, it would not take big O of n. And let's quickly see the coding solution for this one. Okay, so we are going to use a helper method called count good nodes to keep track of the good nodes we have been able to identify, and we are going to pass in the root value we found so far. Now this count good nodes is actually going to return an integer value that defines that how many number of good nodes we have been able to identify for this particular root node. Then we are in the initial input, we are just returning like the minimum value possible, because root in itself has to be greater than that. So root is going to be the first good node. Okay, now we are going to check, okay, that we are taking in as an input the tree node and the maximum node so far. We are checking for an edge case that if the given node is equal to null, we can simply return this 0. If that is not the case, we need to initialize our count to 0. Then we are going to check that if the given current node value is greater than the maximum value we have been able to identify. If that is the case, then we are going to update the counter to 1. And we are also going to update the maximum so far to the current node that we just found out. Once again, we are going to repeat the same process for the upcoming subsequent left child and for upcoming subsequent right child, and we are going to add the values of the left child and right child to our existing count value as well. So whatever count they come back with, we are going to add them to our existing count, and in the end whatever the final count we found, we are going to return that, and that would be written as part of the answer for this one. So that's it. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster, which is pretty awesome, because this has to be some of the fastest code, because the runtime is also not 0 millisecond. So we are doing something really awesome over here. Once again, solution is posted on our GitHub repository, so feel free to go ahead and check it out. Thank you.